So here we are. So thank you, everybody. Good morning. My name is Felix Vega. I work at the Technology Innovation Institute in Abu Dhabi, here in UAE. Thank you for the invitation to be here today and to present these results on the use of artificial intelligence for anomaly detection and spectrum monitoring. So some of these topics have been discussed here today, and I want to share with you what are the, let's say, updates we have regarding this topic here in Abu Dhabi in UAE. I think a little introduction is needed in this forum because you guys are the experts in and the main source of information for us on how the spectrum is critical for all the things that are moving today the economy. However, you guys also have been, let's say, very clear, and many regulators also, on how legacy spectrum monitoring technologies are not keeping up the pace of these new kind of threats and the new kind of technology that have been developed. So congested radio frequency environment is rising, and the interference poses many risks. Critical for the aviation, critical for the energy sector, for defense applications, and for national infrastructure is to have a spectrum that is out of interference and where we can act quickly in order to correct any malfunctioning or any interference presented. Regulators and companies need faster detection and higher accuracy and automated processes. And here is where artificial intelligence can give a hand to produce a more, let's say, automatized and a more safe and especially a more scalable way of doing this kind of processes. Current limitations of radio frequency monitoring systems are mainly known in the community. So we have a high false rate of alarms. So for example, if you are using threshold-based detection, you need to adjust the detection thresholds every time the processes change, or anytime you have a new threat coming, you need to adapt to it. Slow decision cycles are given our legacy of manual classification algorithms, or when you have to intervene, when you have a human in the loop, of course, this is going to take a little bit more time. And of course, there is a slow reaction to new threats. So every time a new threat comes, or a new interference, or a new source of perturbation comes into the environment, well, you need to produce a new mechanism for detection, and you need to adapt basically to this new threat, which is complex because in order to identify something as a threat, you need to first identify the source of the interference. Scale limitations, of course, are due to having to have humans in the loop. This, in a point-to-point, let's say, scenario is going to be easy to undertake. When it takes to a regional level, this is going to be even more complex. And of course, with the increased use of spectrum and this increased utilization, especially in scenarios like yours, and where you have shared spectrum, well, these risks are going to be, or these limitations are going to be every day more present. How can artificial intelligence be used for spectrum monitoring? So on this, I know that there is a lot of research going on in the world right now, and there is a lot of interest from the regulators and the governments on how to integrate these promising technologies into something that is of the day-to-day for the operators. So there are several ideas in place on how to use this. For example, in automatic detection, in order to detect unknown or low probability signals in causing interference. The second point, or the second, let's say, approach, which is the one I'm going to talk a little bit more during the talk, is work in something called anomaly detection, where your system learns from the environment, and once he is aware of how the spectrum behave, every time it found something that it doesn't correspond to this pattern, then it acts or produces a set of alarms. So interestingly, if the system learns what is the normal, it always is going to tell you when is the abnormality coming. And there are ways of doing that. I'm going to go into details in the next slides. Signal classification, of course, is one of the things we all want, because we want to know, for example, what is the data rate, modulation, and historical patterns. And of course, the role of AI in spectrum management is also something that we all want to see some progress, because we can automatize the management of the bands using this kind of automatic devices. And finally, smart decisions. So if we have all this set of tools, we can have a more, let's say, reasoned management decision using automatized tools like this. So in our proposal of how can an AI-driven system architecture looks like, so we think that there are effectively, like in any other system, 4 main components. You know, a sensor network. Nowadays we have wideband software-defined radios, fixed and mobile units that are more affordable and can scan, let's say, in real time, vast swaths of spectrum. We have, of course, a layer for data capturing, and where we have, you know, the possibility of capturing the IQ data of the spectrum and let's say transform this into a matrix or a numerical array that then is plugged into an AI interface that is going to take all these aspects into account, like the spectrogram, the IQ data, the cyclostationary processes, and so on. Finally, well, you have an action layer that is going to give you either automatically or with a human in the loop the information you need in order to take an action. So these 4 components are classical in any case in many of these systems. So what we are discussing now is how to integrate the number 3 is how to integrate the AI component into the loop. So how this anomaly detection works, because generally I'm going to be a little bit, going to take a couple of minutes to explain how this works, because sometimes for the non-specialist, it's a little bit curious to understand how these systems can work and how they are trained. So I am presenting here one of the architectures called an autoencoder neural network. In an autoencoder neural network, we have, this works well. We have a training data set, which is a numerical representation of whatever you are trying to identify. For example, a numerical representation of an image, or a numerical representation of the spectrum content in a certain amount of time. So this training data set, the normal, it's passed through what is called a neural network encoder. This neural network encoder takes this data set. You have here let's say, numerical points, and this encoder, let's say, reduces the dimensionality or reduce the number of points that are in the training data set into something that is called a compressed representation of the data set. A compressed representation is not anything else that the same data set with a lower number of points. So this lower number of points represent the input data set, and then you have a second neural network that can, with this smaller number of points, reproduce the input data points. So at the end of the day, you have the T matrix, which is the data points you use for training. You have the reconstructed data set, the R matrix, and if these 2 matrices are smaller than a certain threshold error, then this output corresponds to this input. And bingo, what we can say during the training is that these systems learn how to transform these complex data sets into something less complex, and then how to decode this into representation of the representation of the training data set. How this is used? So in the training data phase, you train the system to always reproduce what is normal, And in the utilization data phase, in the utilization phase, you have new information that is entered into the encoder. And when the things are normal, my encoder is always going to be able to reproduce the signal that he knows exists. But when you have an anomaly, when you have interference, for example, the reconstructed data set is going to be different to the input data set. And at that moment, the system is going to say, hey, there is something here that I don't understand how it works. This approach has been used for many, along many researchers along the world for this kind of anomaly detection in other contexts. We are using it now at the Technology Innovation Institute to reconstruct or to determine when a data set is corrupted by noise in spectrum monitoring. This is what can be the training data set, can be IQ data or can be spectrograms. There are many different ways of doing that. So in this approach, the anomaly detection, we have, let's say, four stages that are represented in the image. So we built a data set, a huge data set of the normal activation or the normal representation of the spectrum. So we did this as a waveforms experiment I'm going to show you later with Wi-Fi. So we did a large data set of collection of Wi-Fi signals in a normal environment. Then we converted the data sets, converted the IQ into FFTs and the FFTs into a spectrogram. So the spectrogram is a representation of the normal way the spectrum looks. And with this data analysis, we did a data training that was able to segment, which is the thing you want. You have here in this K-means representation, you have normal Wi-Fi transmission, you have Bluetooth signals, and you have an anomaly that it doesn't correspond to any of these two. So these anomalies are red flagged, and this is the thing that anything that doesn't correspond to any of these two normal behaviors is going to be flagged as an anomaly. This is the kind of figures you always find in these autoencoders neural networks that are representing the reduction in the dimensionality and then the expansion with the encoder dataset. This is one of our let's say summarizing one of the capabilities we have at the Technology Innovation Institute in Abu Dhabi. So we can do all these things like modulation classification, detection of abnormal patterns, and prediction of interference hotspots, and geolocalization using TDUIA algorithms. I think this here, it's a video I'm going to show of how does it look. It's just, let's say, it's a little bit abstract, I will say, but this up, whoops. How do we press enter here? Maybe in the cabin can help us upstairs, because I cannot. Yeah. Maybe upstairs they can help us to press enter. Yeah. So here you have the video of the spectrogram already trained the system, and you have normal, let's say, operations. And at some point, you have these lines that are representing chirps that are introduced into the system, and automatically you have a red flag telling you there is something abnormal into the system. So here we are using chirps, which is a very basic waveform, just to represent in a, let's say, exaggerated way in the spectrogram that you can see that there is interference. But the levels of interference, the type of signals, the duration of those signals, they can be whatever you want, as long as this is not something that the system knows, then you have this possibility of using these tools to detect interference. This can, this is it's a short video to represent that. The experiment was conducted using a larger data set of points in a Wi-Fi scenario, a normal Wi-Fi scenario, and then once trained, we introduce artificially the noise of interference to detect the anomaly. It has been done over the two versions of Wi-Fi 2.4 and 5.5, but it's easily expandable using the right tools to more spectrum. The implications of the applications of this, well, they are very well known. They can be used in national spectrum regulation. They can be used for observation of aviation, traffic, smart cities, defense, and 5G, 6G, and private network. This is basically what I introduced in the beginning. And what are the regulatory benefits? Of course, is faster enforcement, because these kind of tools can give you let's say, alerts and alarms of not authorized use of the spectrum, can do automatic tracking, and can improve the efficiency of the policies and the efficiency of the policies implemented in the country. So far, we have been training this system with Wi-Fi signals, where we have a couple of demos with 2 countries in Africa, where we are applying this to the surveillance between the border between 2 countries to first see how the shared spectrum is used, and second, to detect unauthorized use of the spectrum in regions where there are safety problems, security problems. These are ideas on how people is thinking these tools can be used in our sector. So for autonomous spectrum allocation, so you can have these tools running in the background and another tool taking decisions on how to allocate the spectrum. You can use also generative AI models to generate synthetic signal training. Collect this amount of data requires a lot of time. So this simple demo requires 7 terabytes of collection of data for training. So having tools that can generate synthetic data is a very good idea. Fully AI-native regulatory frameworks, for example, is an idea for the UAE. And having satellite integration for full coverage can be done if you use this kind of tools. This is my last slide. Thank you very much. I'm open for questions.